I want to go over an example problem to illustrate the strict definition that we have so far for average velocity. So from the previous video lessons, you learned that average velocity is defined as being equal to some total distance divided by the total interval of time it takes to cover that distance. So as an example, consider a trip you might take. Maybe you jump in a pickup truck and you drive down the highway, and it's a fairly long trip. You go a total of let's say 120. Yeah, you go 120 miles. But there's a lot of traffic when you first start out. In fact, the first half of your journey, for the first 60 miles, you go at a steady 20 miles per hour just because of the traffic. And then all of a sudden, halfway through the trip, the traffic eases up, and for the next 60 miles, you're able to travel at a speed of 60 miles per hour. My question for you is, what's the average speed for this whole trip? What do you get when you spend half of a trip going 20 miles per hour and the other half of the trip going 60 miles per hour? So why don't you do this? Hit pause, take as long as it requires for you to make a calculation, and scribble it down on a piece of paper. If you need to hit pause to do this, so hit pause and then resume as soon as you're ready to give an answer. Okay, so welcome back. Let's see what you came up with. I'm going to guess that some of y'all might have said that the answer, I don't need to pause to write this down. I can do it off the top of my head. The average of 20 and 60 is 40. 20 miles per hour plus 60 miles per hour. Add the 2 and divide by 2. Sure, I'm going to get an average of 40 miles per hour, end of story. So you might be surprised to find that that's incorrect. Those who took this definition to heart found a different answer, right? So let's see. We know the total distance traveled. That's easy. That's given. That's 120 miles. We don't know the total time, but we can figure it out. If you have to go 60 miles and you do so at a speed of 20 miles per hour, I think we all agree that's going to take 3 hours for the first half of the journey. And likewise, the second half of the journey, 60 miles at 60 miles per hour, is only going to take 1 hour. So if we add this all up, our total time is 4 hours. And so it turns out the average speed isn't 40 miles per hour. It's quite a bit less. It's 30 miles per hour. Now, if that surprises you, let's try to clear this up by making a graph to illustrate what the motion of this truck would look like when plotted as a speed versus time or velocity versus time graph. So let's see. It took 4 hours, so let's go 1, 2, 3, 4. The speed started out at 20, and then 40, and then 60. Okay, so the units here for speed are implied as miles per hour, and the time is implied as hours. So here we go. The car maintained 20 miles per hour for the first 1, 2, 3 hours, right? And then all of a sudden, boom, right at this spot, the traffic cleared up, and in an instant, the truck speed increased up to 60 miles per hour, but only maintained that for a time of 1 hour. So this is not very uniform. The speed changed in an abrupt manner. It suddenly went from 20 to 60 all at one instant in time. So that's part of the answer to why we can't just take an average by adding the two quantities and dividing by 2. A side note, I'm going to draw a different graph. This is just a totally different hypothetical situation. But I'll remind you, in the previous video lesson, we were looking at position versus time graphs instead of velocity versus time graphs. And so maybe there's an object, it doesn't matter, maybe it's a squirrel that's running down the sidewalk or something like this, and it moves like, oops. Maybe it moves like that. Okay, so definitely not a steady speed. Certainly doesn't hold a constant position, right? Holding a constant position would be a graph like this, just always staying in the same place. Let's say, what's the speed of this squirrel at this point in time compared to what it was at this earlier point in time? And so we know at which point in time the speed was greater. We just have to compare the slopes of some tangent lines. So this earlier moment in time, the speed was significantly greater than it is here. In fact, here, the squirrel almost came to rest at this instant in time. Just very, very slight slope there. My point here is that this is a graph that at face value is only trying to tell you about position. It's only trying to give you the meters as the time goes by. But if you're willing to do some calculation, a graph of position versus time also indicates speed if you're willing to make a calculation of slope. So in the same vein, this graph that applies to our example problem of the truck at face value seems to only tell you about speeds as time goes by. But if you're willing to make a calculation, you can learn more. Now in this case, the calculation isn't slope, the calculation is area. If you're willing to calculate area, then you can figure out distance traveled. In fact, we'll see, this agrees with what we know. If I find the area of this rectangle, well, it's a height of 20 miles per hour divided by a length of 3 hours. So the area is 20 miles per hour multiplied by 3 hours. Hours cancels out. Oh, but we already knew this distance should be 60 miles because that's what we said here. And in the same way, the area of this rectangle, length times width, 60 miles per hour. We don't just multiply the numbers, we multiply the numbers along with their corresponding units. 60 miles per hour multiplied by 1 hour. Hours cancel out, and we're left with, 60 miles. So you can see the area does indeed represent the distance. 60 miles for the first 3 hours, another 60 miles for the last hour, for a total of 120 miles. Now, is there ever a case where you can use the shortcut of just adding two velocities and dividing by 2 to get the average speed? Or do we always have to use this formula? So the answer is you'll never get it wrong if you use this formula to find average velocity. Sometimes, as we've seen, the approach of adding and dividing by 2 will get it wrong. But sometimes the 2 will give you the same answer. So, this is an impossible situation because there's an acceleration that takes place. There's an increase in speed from 20 miles per hour to 60, but if we zoom in, it seems like that increase happened at one single instant in time. In reality, the graph would actually have to look something like this. If the traffic eased up and the vehicle going 20 miles per hour increased up to 60 miles per hour, that can't happen all at a single moment in time. The graph would have to have a little bit of curvature to it. And so if we zoom in, we'd see that from 20 up to 60 actually is stretched out over a time interval. Now, albeit that's a pretty steep slope right here, but it's not an infinite value of acceleration. So let me offer another way that a car might change its speed. It's impossible to do so in a single instant. It's possible, and in fact typical, to increase like this when driving on the freeway, but it would also be possible, although kind of strange, to say you're going to go on a 4-hour trip where you started out at the very beginning, at the very initial moment in time you were paying attention to your motion, you were already going 20 miles per hour, and then the driver of the car very subtly starts to push down harder and harder on the gas pedal, going from 20 miles per hour up to 21 miles per hour. up to 22 miles per hour, and so on. You see where I'm going with this. So that it takes a total of 4 hours to make the increase from 20 miles per hour up to 60 miles per hour. In that case, would we get the same result by calculating delta x over t as we would if we just took the initial velocity and added the final velocity and divided by 2? How do these two answers compare? Oh, and I don't like the way I wrote that. Here, let me change this. Instead of I and F for initial and final, and I kind of spazzed out on my V there, didn't I? We'll say V naught for initial velocity, and then without the subscript means final. So let's do this calculation first. This one's easy. This is 20 plus 60 divided by 2. Oh yeah, so that's 40 miles per hour. Now let's do delta x over t. Well, I know t is 4 hours. I don't know the distance traveled, but if you take my word for it, that whenever you make a graph of velocity versus time, the area is a way of indicating the distance traveled, then let's find the area bound under this graph. Let's divide it up into two parts. Let's find the area of the rectangle and add to that the area of this triangle. So the rectangle is easy. You all agree with me that that's just 20 times 4 to give us 80 miles. And then the area of the triangle, let's see, 1/2 base times height. So 1/2 times 4 hours times, what's the height? It's not 60, it's starting at 20 and going up to 60, so I believe this height right here is a height of 40, yeah. So 40 miles per hour. Again, I'm not just plugging in numbers, I'm plugging in numbers as well as their units to see how the units cancel out. Hours cancel hours. Let's see, so 4 times 40 would be 160, and half of that is 80. Oh, so the triangle and the rectangle both give me the same value. Okay, so we have a total distance of 160 miles, and 160 miles divided by 4 hours is indeed 40 miles per hour. So the difference between this graph and the one in our original situation is this is a non-uniform acceleration. What I mean by non-uniform is it wasn't spread out and gradual. The speed changed in an instant, where here, for every moment that goes by, the increase in time leads to the same increase in speed. So back to the first graph, if I go forward for 10 minutes, 0 increase in speed. I go another 10 minutes. In that 10 minutes, 0 increase. And I keep doing this, so the increase in speed for every little interval in time is 0. And then all of a sudden in this interval of time, there's a very large increase in speed, and then we're back to no increase in speed. Whereas on this graph, I go forward a little bit in time, and there's a little bit of an increase in the speed. I go forward in time again, and there's the same increase in speed. And I go forward again. There's a continuous steady slope to this graph. In the same way that the slope on a position versus time graph tells you about the speed, the slope on a velocity versus time graph is an indication of acceleration. So we're often not just looking at the values plotted on a graph. We're also looking at areas and slopes as a way to find out more from the graph. So in any case, this is a uniform acceleration. So we've got a special situation here. If acceleration is uniform, then delta x over t and v initial plus v final divided by 2 both yield the same result and give us a way of finding an average velocity. So, if that's the case, let's set these two expressions equal to each other. If delta x over t and adding the initial velocity and final velocity divided by 2 are both ways of calculating average velocity, then I can set them equal, and I can do a little cross multiplying here. Let's just multiply both sides of this equation by t, and we end up with delta x is equal to, I can pull this divided by 2 out and say that's the same thing as 1/2. Put this in brackets. So this is 1/2 v naught plus v multiplied by t. Now at this point, this should be familiar. I've referenced this a few times already this semester. This is one of the 4 kinematics equations that we're going to apply when we get to the point of problem solving, which is coming up here shortly. So there it is. There's one of our 4 kinematics equations. Now I challenge you to see if you remember any of the others, because they've been stated a couple times now. You might know this other one says final velocity is initial velocity plus acceleration times time. Let's see, do you know the third one? Distance traveled is equal to initial velocity multiplied by time plus 1/2 times acceleration times time squared. Some of you know a fourth one. Final velocity squared is equal to initial velocity squared plus 2 times acceleration times distance. Now, you're no longer allowed to ask me where this equation comes from. It comes from the fact that as long as acceleration is uniform, I can say the 2 methods for calculating average velocity are the same. So I need to make something very clear at this point, and this is a big red alert. These 4 equations are not universally true. These 4 equations only apply to uniform accelerated motion. However, as you know with the ruler drop experiment we did, when gravity causes an object to accelerate, the acceleration is indeed uniform. So there are quite a few examples in our world of uniform accelerations. And whenever we have that type of motion, we can apply these 4 equations. One of the 4 equations, you know where it comes from. It's just based off of our definition for average speed. So in the next upcoming video lectures, I'll try to give an explanation of where these other 3 equations come from.